Hello and welcome to this lecture. In this lecture, we're going to start looking at how to play around with matrices, right? So, if you have uh, many matrices, you may want to add them, multiply them, see if they have an inverse. You can take powers of them, much like you do with numbers. You can do quite a few operations with matrices, and that's what we're going to see starting with this lecture. Okay. First thing is addition of linear transformation and the corresponding addition of matrices. When you have two linear transformations going from the same Fn to Fm, okay, both have to be the same, otherwise adding doesn't make too much sense. You can naturally define an addition. So, T1 plus T2 will be what? Will be another transformation which goes from Fn to Fm. And how do I define it? For a particular u, T1 plus T2 when it acts on it, it simply does T1 of u plus T2 of u. Okay, so this is also a linear transformation. It's very easy to see, straightforward addition. And if you look at it in the matrix world, if matrix of T1 is A11 to AMN and matrix of T2 is B11 to BMN in this matrix, the basis has to be common. Okay, only then it makes sense to think of them together. You know, if you keep changing the basis here and there, then things change quite a bit, but you keep the basis the same, and then when you decompose u with respect to this that common basis, you will get very similar matrix addition, and matrix of T1 T2 with respect to the same input output basis will become the same. So, most of the cases we will be dealing with canonical basis. So, I guess in canonical basis, if everything is with respect to canonical basis, you have just the addition of the operators, and that addition of the transformations and addition of the matrices are exactly the same. Okay, so clearly addition works. You can also do scalar multiplication. I don't have a separate slide on this, but if you have C times T1 is simply C times this matrix, right? When you say C times this matrix, every element of this matrix is multiplied by C. Okay, all the elements are multiplied by C. So, that's scalar multiplication. So, you can add two matrices, you can multiply a matrix with a scalar and so on. Okay, so that's one. You can also compose two linear transformations. We saw this earlier in the F2 case. It was very simple. In this case, when you have more generality, you have to be slightly careful about composition. Notice what happens here. Notice how these M and N, M and F, K and N work. Okay, T1 goes from Fn to Fm. Okay, vectors with N coordinates to vectors with M coordinates. So, that is T1. Okay, notice how T2 is. T2 goes from K coordinates to N coordinates. Okay, so T2 takes an input from Fk and puts and its output is in Fn. T1 has an input in Fn and output is in Fm. Okay. So, in this situation, when the output of T2, the space of output of T2 matches with the space of input of T1, you can do a composition. How do I define the composition? Composition of T1 and T2 denoted T1 circ T2. It is basically defined as a transformation from a vector u which is in Fk to T1 of T2 of u. Okay. So, notice how this is working. T2 of u would take u from Fk to Fn, and then T1 works on vectors in Fn, right. So, T1 will send that T2 of u to a vector in Fm. So, this overall T1 circ T2, T1 composed with T2 is a transformation from Fk to Fm. Okay. So, this is how it works. U under T2 goes to T2 of u, and then T2 of u under T1 goes to T1 of T2 of u. And like I said here, I've shown this in circle. These two have to match for composition, otherwise composition doesn't make sense, right. So, you can't compose two things which are not compatible with each other, as in the inputs and outputs should sort of match. Okay, so this is how this works, and it's very easy to show that T1 composed with T2 from Fk to Fm is a linear transformation. The proof more or less is exactly similar to what we wrote down in the F2 to F2 case. It's just writing down the exact same thing. Okay. So, I hope this is clear. So, composition in the general case needs this additional criteria that the output of the first guy should be the same as the input of this guy, right. The spaces should match. Okay. So, this is composition, simple enough. Okay. Now, we are interested in the matrix of the composition. So, you have matrix of T1 here, matrix of T2 here. Like I mentioned, the basis of Fn needs to match with the basis of Fn in general on these two guys, but anyway, we are going to pick canonical basis throughout. So, these basis issues won't come for us. Okay. Now, how do I think of the matrix of T1 composed with T2? It's the same as anything else. See, T1 composed with T2 is a linear transform from Fk to Fm, right. So, I have to take each input basis vector here of Fk, which is a canonical basis, right, E1, E2, still Ek, and find out its output according to T1 composed with T2. So, basically I have to first find T2 of E1. Okay, what is T2 of E1? If I do E1 to T2, how did I find M of T2? The first column, right? So, T2 of E1 is the first column here. T2 of E2 is the second column. T2 of Ek is the last column, right? So, that is how matrices of a linear transformation are defined. Okay. Now, T2 of E1 is the first column. Now, when T2 of E1, the first column is given as input to T1, the output will be this matrix multiplied by this first column, right. So, this first column. So, T1 of T2 of E1 is what I am trying to find. So, when E1 goes in, I get this column as output with T2, and that column goes as input to this. So, this matrix will be multiplied on the right by B11 to Bn1. That will be T1 of T2 of E1. So, that is what is written here. Okay. T1 of T2 of E1 is T1 of this first column, right. So, T2 of E1 is just this first column, and then T1 of the first column is what I need to evaluate, and that is nothing but this matrix multiplying this with this vector on the right, right. So, that will be just B11 times this first column here plus B12 times the second column here, so on till Bn1 times the last column here. Okay, I hope that is clear. So, that is what this T1 of T2 of E1 is, and now you can multiply it out and add it up, and you will get A11 B11 plus so on till A1n Bn1, then the last row will also be like that. Okay. So, I hope this is clear. So, this is just a computation of T1 of T2 of E1. Now, I can repeat this for T1 of T2 of Ei, the ith basis vector. Now, T2 of Ei, the ith basis vector will be the ith column here, right. The ith column here is B1i to Bni, and T1 of B1i to Bni, and I am going to repeat the same thing here. So, it is B1i times this column plus so on till Bni times this column, and I can simplify and write it like this. Okay. So, every column of T1 composed with T2 can be found like this. Okay. Now, to find the final matrix, it is just a question of putting this all together. Okay. So, the matrix of T1 T2 from Fk to Fm is a k by n matrix. Okay, and the matrix of T1 T2, every entry will look like this, right. So, the first row was this, and you can go through and find out that every entry will look like this. I hope this is clear. So, you see the first column, we found the first column, so you can go and see the first column was this, the ith column was this. So, I have just repeated the same thing column by column. So, the first column was this guy, second column, and the last column was simply this guy. Okay. So, I hope this is clear. So, it takes a little bit of time to get used to it. How do you compute this? I will give you a few more ideas on how to compute this, but nevertheless, this is the definition of the matrix of T1, T2. Okay. The ith column is simply what we computed earlier. Okay. Column by column, you can compute the multiplication. So, you take this first column, multiply on the right, you get the first column here, the ith column here, multiply on the right, you get the ith column of the product, and that is how the matrix of the composition T1 circ T2 is computed. Okay. So, now there is a connection with matrix multiplication. In fact, matrix multiplication is defined as the matrix of the transformation. Okay. So, when you have these two transformations T1 T2 and the corresponding matrices, if you have an input u, okay, going into the composition, if you want to compute T1 of T2 of u, it is the same as the matrix corresponding to the T1 circ T2 u, right. That is what it is. This is the way in which we define the matrix. Now, this T1 of T2 of u, what is T2 of u? It is M of T2 times u, right. M of T2 times u on the right. Okay, as a column vector, you can put down u, you will get that. Now, T1 of something is this matrix multiplied by M of T2 u on the right. Okay, so you get M of T1 times M of T2 u on the right. So, that's what is going on here. So, you see here that M of T1 composed with T2u is the same as M of T1 times M of T2u. Okay. So, this gives you a very clean definition of the multiplication of two matrices. How do you multiply these two matrices? First of all, these conditions should match. This Fn and Fn should match. The number of columns here should be equal to the number of rows here. This n should match. Only then a multiplication is valid, and the multiplication is simply the matrix of the composition T1 circ T2, which is just, you take this column, multiply with this matrix on the right, write that as the first column here, so on so forth till the last column. You take this column, multiply by this matrix on the right, you get the last column. Okay, column by column, you can proceed in this fashion. Okay, so this is the definition of matrix multiplication. So we knew how to add matrices, we know how to scale matrices. Now we know how to multiply matrices also. But the thing is, for multiplying matrices, you need this other condition, right? The number of columns of the first matrix and the number of rows of the second matrix should match. Only then you can multiply. Okay. So there's various ways to compute the matrix multiplication. First way to compute is element by element. Okay. How do I do that? You can take the first row and the first column, and that together gives you the first element here, right? So you multiply the corresponding elements and add them. It's sort of like a dot product. Okay. The first thing is a dot product of the first row and the first column. The second entry, likewise here in the first row, will be the dot product of the first row and the second column. First row and the third column, first row and the last column will give you the last element here. So you can go element by element, row wise, and simply do dot products, dot products, dot products, dot products, and you will get all the entries in the first row. So now you come to the second row. You take the second row here, take dot product to the first column. That will give you the second entry here in the first column. So on. Okay, you can fill in the second row. Then you take the second row, dot product to second column, second row, dot product to third column. That way you can do dot product to evaluate element by element. That's one way to do it. Okay. Another way to do it is to do row by row. This is row wise. So you take A11, multiply by the first row here, multiply the first row here. Then plus A12, multiply the second row. So on till A1n, multiply the last row. Okay. And then add all those row vectors together, you get the first row of the product. Okay. So you can multiply and compute like this for the entire first row. How do I find the entire first row of the product? I take the first element, multiply with the first row, second element, multiply with the second row, so on till last element, multiply with the last row, and then add up all those multiplied row vectors together, you get the first case. So likewise, you come to the second row, third row, and the last row is clearly like this. Okay, so you can compute this matrix row by row in that fashion. So you notice here that every row of the product is a linear combination of the second matrix, rows of the second matrix. Okay, that's an important property of multiplication. You can also do column wise. We saw the column wise before. You take the first column here and multiply by the corresponding columns, each of those columns by the value here, and then add up all those columns, you get the first column of the product. Likewise, you can do and repeat throughout. So you see the columns of the product are actually linear combination of the columns of the first matrix. Okay, so that is also an interesting property of multiplication of matrices. So this is how you multiply. Again, the condition is important. Number of columns of the first matrix on the left should match the number of rows of the second matrix on the right. Only then multiplication is feasible. Okay. So one interesting property of composition is that it's associative. What is associative? If you have T1, T2, T3 being three operators, you can define T1 composed with T2, T2 composed with T3. Okay. Let's say these two are well defined. Okay. Then it turns out T1 composed with T2 composed with T3 is defined, and it's also T1 composed with T2 composed with T3 also is defined. Okay, so think about why these things are defined. The inputs outputs will match, right? See, the output of T2 matches with the input of T1, output of T3 matches with the input of T2. Okay, so you can keep doing these compositions. You do this composition first, and this output will be the same as this input, and it will match. Okay, all these outputs and inputs will match. So I can do compose one after the other. Since these two are defined, it is also interesting that these two are equal. Okay, it doesn't matter whether you do this first and then do u, or that first and do u. You see that for any input u, this kind of composition, three-way composition, is the same as T1 of, T2 of, T3 of u. You hit u with T3 first. Whatever happens, you're going to hit u with T3 first, and then T3 of u is going to be hit with T2, and T2 of T3 of u is going to be hit with T1. It doesn't matter whether you group like this or group like that. This kind of a property is called associativity. So basically, once it's associative, you can drop these brackets. These brackets are not needed. You can just write T1 composed with T2 composed with T3. So it's very, very interesting to see matrix multiplication is associative, but it's not commutative. We've seen very clear examples for how matrix multiplication is not commutative, but multiplication is indeed associative, as long as it's well defined. Okay, so it has to be well defined. But if it's not well defined, as in the number of columns and rows don't match, then you get into trouble. Otherwise, it is associative. Okay, so this is a good property of matrix multiplication. Here are a few simple examples just to get your feet wet. You can see here, this is a 2 by 4 matrix, this is a 4 by 3 matrix. you multiply, you're going to get a 2 by 3 matrix as the output, and you can do the multiplication in element wise. Take a dot product here, put the first element, dot product here, second element, dot product here, third element in the first row, and then you take a dot product here, first element in the second row, and so on. So, this is basic stuff, you can quickly do it. There are very interesting looking dot products like this, which is row vector multiplied by a column vector. This will give you a scalar, right? This will be a scalar value, 1 by 1 value, right? So, this column vector multiplied by a row vector on the other hand will give you a 4 by 4 matrix. Okay, think about why that is true. This vector multiplying this vector, right, will give you, like, the first row will be just this multiplied by this 1 2 1 2, second row will be 2 4 2 4, third row will be 1 2 1 2, last row will be 0 0 0 0. So, there will be a 4 by 4 matrix here. This will just be a scalar, just a dot product of these two, 1 plus 4 plus 1 plus 0. So, you will get 6, I guess, as the answer here. 6 is the answer here. This one is a 4 by 4 matrix. Okay. So, look at this question. For what size of matrices AB will both AB and BA be defined? Okay, think that through very carefully. You want AB to be defined and BA to be defined. So, it will happen only if A and B is sort of like our transposes of each other, as in A, the sizes should be transposed. So, A is, suppose A is m by n, B has to be n by m. Okay, only then both AB and BA will be defined. Okay, so for instance, A could be 2 by 4, B has to be 4 by 2, right? It cannot be anything else, right? So, that is very interesting thing to see, that AB and BA can be defined, but they will all be, they could be different actually, right? Sizes itself could be different. Like for instance, if A is 2 by 4 and B is 4 by 2, AB is 2 by 2, BA is 4 by 4. Okay, the sizes itself are different. Okay, so that sort of quickly concludes the algebra of matrices and addition, multiplication, basically both addition and multiplication, how to do that, and that's the end of this lecture. Thank you.